So here are some limitations of Google. I've spent my entire life searching for meaning, and the child says, my dad says, if it's not on Google, probably you won't find it. I put these cartoons up because I think that there are some challenges ahead. Google is not omniscient. Google is not God, and it's very important to realize that Google has its limitations. This is one of them. And therefore, the future scientific community must address the defects of Google, which I will highlight in this particular talk. Here's the web at a glance. So let's try to understand how Google works. Here's the user puts in a query, and the query goes to a search engine. The search engine then looks at all its stored document IDs for that keyword, which have been already collected beforehand. It has nothing to do with your keyword. Google continuously, every 2 minutes or 3 minutes, crawls the web and collects all the PDF web pages and photographs them. And so it's stored in a database. So whether you like it or not, that's what's happening. Crawls the web. These document IDs are then stored in this spot. They're also sorted by some sort of inverted index. I mean, there's some sort of cross-correlation keyword indexing going on so that it makes it a little bit faster. Now, the rank results are using this data plus the mathematical algorithm, which I'll outline. So that's the query. This part of the thing is query independent, and the query promotes the ranking, and that's what's called the PageRank algorithm. So let's look at the web as a directed graph. The graph here, by the way, is not the XY axis in the picture that function that I'm talking about. Graph is a combinatorial concept, combinatorial tool in which we represent some phenomenon. It could be railway networking, timetabling, the spread of diseases and whatnot. All sorts of things can be modeled using a graph. A graph is a collection of vertices together with a bunch of edges. The edges depict or denote some sort of relation between the two vertices. The vertices, of course, represent certain things. So the edges are the links coming out into the web page and going out of the page. Coming into the web page and going out of the web page. So we may have what's called a directed graph. You have two vertices, you have an edge joining one vertex to the other, and we can put an arrow on that edge to indicate that somehow there's a relation in that direction. So when you try to draw the World Wide Web as a graph, so what you would do, each URL would be a node vertex, and then it will be connected to another vertex if this particular node points or has a link to the other. That's how you would draw the graph. Of course, it's a huge graph and you would never draw it, but I'm just telling it to you as an abstract idea. This is not what Google does, by the way. I'll tell you in a second what Google does. Here's the PageRank algorithm. It was discovered by these two people, Sergey Brin and Larry Page. They were PhD students at Stanford University when they got the idea. The professor was talking about the Perron-Frobenius theorem. And they immediately recognized how the Perron-Frobenius theorem can be used to create a ranking of search engines, and immediately ran off. They dropped out of the PhD program, and I don't think they got back in after that. Their idea, while listening to this lecture by the professor, math professor actually, talking about the Markov chain process, they realized that you can measure importance by this axiom. Why in real life, what is considered important? For example, in the scientific community, how do we designate that a certain particular scientific paper is important? Not everybody in the scientific community has read the paper to certify that the paper is important. Probably only a few experts have. But their expert testimony somehow carries a little bit of weight. And of course, there are positive aspects and negative aspects. One only needs to consider the work of Blavatsky, who got the Fields Medal, and it's now clear that much of that stuff is a little dubious. So it's not clear exactly whether this peer review process is infallible. It's not. It has its shortcomings. However, these people took this idea of the peer review process as the definition of importance, because that's in life, in real life, that's what we do, unfortunately. We rely on other people's testimony to certify whether some paper is important or not. So the algorithm was patented in 2001. So Google is actually relatively young as opposed to the other search engines. Here's the example of how Google works. I just picked a bunch of websites here, and you can see the website B and the website C seem to be pretty important, more important than the other websites. Well, the fact that website B is important is clear enough because there are lots of other websites pointing to it. Right? That's clear enough why that should be important. But the website C now is also important because an important website is pointing to it. Okay, so this is the idea of importance. And is it possible to model this definition into some sort of mathematical equation? So essentially, Google is a popularity contest. That's what it is. It's a popularity contest. And that's one of the important shortcomings of Google that should be addressed, because it's possible that there's a fundamental paper out there that hasn't been read by all the experts, or they haven't certified it. It has happened in the history of mathematics itself. So this is not a completely foolproof method of measuring importance. So how do we formulate? Okay, but it's a start. And if we take it as a start, and I think most of you will agree that Google does have its positive aspects, and somehow it seems to work maybe 90% of the time. So let's see how to formulate this mathematically. I told you about the graph. So here's a toy graph with 3 vertices, A, B, and C. And we have several edges coming out of A to B, A to C, and B to A. So here, the out degree of A is 2, meaning there are 2 edges coming out of A. And the in degree, designated as degree minus here, is 1, because there's only 1 edge coming in to the vertex. So let R of J be the rank or the importance of page J. Then their definition is a page is important if other important pages are pointing to it, right? So how do you measure that? Well, for each page, we have the designation of a rank. The rank of the K is going to be the sum of the ranks of all the pages pointing to K. That's the idea. Now, this out degree is going to be the probability. So that means if I'm sitting at the vertex J, J is actually pointing to K. But J is pointing to some other things too. So what is the probability that I will end up at K if I'm sitting at J? Well, it's equal to 1 over the number of edges coming out of it. So 1 over the out degree. So that's what this thing is. So So that's what this thing is. This is the probability. 1 over the degree plus degree of J is the probability that if I'm sitting at J, I end up at K. Okay? So the rank of J is the importance of that. So the total probability of that particular page is that, and therefore this is how we're going to measure. Now notice it's a kind of a recursion. It looked circular, right? The definition, why is something important? It was important because other important pages were pointing to it. Sounded like a circular definition. But that circularness of the definition is a common thing in mathematics. It happens all the time in matrix algebra. So some matrix is defined in terms of other things in some sort of recursive way. So this is basically formulated using matrices. So here's a simple quick history of matrix theory. Matrix theory was discovered by Hermann Grossman, who was a mathematician, but unemployed mathematician, believe it or not. The interesting thing about Grossman was not only was he a true mathematician, but he was also a true Sanskrit scholar. Apparently, he was an expert in Sanskrit, and he translated the Rig Veda into Sanskrit, the first translation. And he was well aware of the origin of words, and he was enamored by the word matra, which is, of course, the Sanskrit word for mother, and decided to name his new invention, the matrices, using matra. Matra is the root word